Okay, so in this next set of videos, we're going to start looking at Unit 4, which is systems of particles and linear momentum. It's, again, after this, we have just a handful of units left. And so this is the first topic we're gonna look at is center of mass. And so this is a new topic. It may have been briefly discussed in Physics 1, but here we're going to really dive deeper into what center of mass is, how do we calculate it, how does calculus play into this. So what happens is up until now, the study of kinematics, forces, energy, all of our focus has been the idea that motion is going to be done by a single object, right, or a single particle. So if we were talking about a car traveling, we treated that car as a single object. We didn't care about all the little pieces of the car. But what's going to happen is now we're going to start treating these particles as systems of particles. And this is kind of where the calculus does come into play, right? Because essentially what we're going to do is we're going to break up all these particles into an infinite amount of masses and so forth, and that's going to bring in the concept of integrals. Right, so systems can have really two things. It can have a finite set, which has a finite number of particles, which means it has a set amount of particles, or it can have an infinite number of particles, right? And so just a couple examples. So let's just say I have, right, a set of 42 rocks. I know 42 just seems like a weird number to go with, but the idea is that we have just this set amount of rocks. So if I told you we had 42 rocks, in your mind you can picture what does 42 rocks look like. Okay, and then on the other side, right, and so this would be our finite example. Right, now on the other side we're going to look at like an infinite would be like a meter stick. Right, and a meter stick may seem like it's a finite set of particles, right? But it's actually, a meter stick has an infinite amount of particles that are inside of it. Okay, and so that's where we're going to make that distinction really between Physics 1 and Physics C. So one thing to note is that for any system of masses, so this is where we transition into our talk about center of mass. So for any system of masses, there's exactly one point that moves as if the entire mass of the system were concentrated in it and all the forces were applied to it. This also, we're going to talk about here in momentum, but also this appears when we do rotation. So there's a very famous picture of a hammer being thrown. If you throw the hammer linearly, the center of mass rotates, or the object rotates about the center of mass. So it kind of looks like short, big, short, big, short, big, but it actually looks like the hammer is actually traveling in an arc, but it's actually the center of mass travels in a straight line. But that's just a rotation example. And so the point that we're just focusing on is what we call the center of mass. Okay, and you're going to see two abbreviations. I like to use COM, but a lot of times in textbooks they just say CM. So I'll go between the two, right? If I'm giving you kind of notes, I'll probably use COM, but if we're talking about like an equation, we'll talk about CM. But they're the same thing. They both mean center of mass. So now if we look at these figures here on the right, and we just say that the mass of the systems, right, and you can see that figure 1 is a one particle system, right? The arrows represent forces. Okay, so this is like F1, F2, F3, and what we're doing is we're applying all the same forces, right, on these different objects. So this is F3, this is F1, and this is F2, right? But you can see how it's different. So the first example would be like, Physics 1. How does this object react when you apply these forces on the object? The second two examples, figure 2 and 3, this is now our our finite example and our infinite example. Okay, so figure 2 is a system of 3 particles. Figure 3 is a system of a infinite amount of particles. So what happens is, in addition to the masses of these systems being the same, okay, and I kind of messed, this document's a little messed up, but what happens is the forces, or the net force, right, which, if we talk about the forces, which means the net force, and net force is not plural, I apologize for that. Okay, so the net force is going to be equal as well, making the accelerations equal as well. Okay, so if net force is equal because the mass is equal, that means that the acceleration is going to be equal. So now what happens is, in figures 2 and 3, it's not necessarily the objects that are going to be, the focus of the acceleration, but it's going to be that center of mass is what is accelerating. Okay, so that's just a quick little example. How does this really work? The next here, associated with the center of mass, is something called the center of gravity. Okay, and so what happens is the center of gravity of a system of particles is defined as the point in which the net force of gravity, right, or we can talk about it being the weight acting on the system, can be assumed to be applied. Now what happens is the assumption that the center of mass and the center of gravity are the same point is not always the case, but because this, we make this assumption because in the universe the difference of the two locations is so minute that they're basically one and the same. So I mean, if I just do like a quick little thing, my center of mass may be here, but what happens is, my center of gravity is like right there, right? So essentially it's the same point. And that's how, that's the assumption that we're going to make for all of these calculations and so forth. All right. Now, to find the center of mass, what you actually use is what we call the weighted, okay, average of the masses for highly symmetrical systems. And so you want to kind of like put quotations around the weighted average of the masses. All right. And so this next example is like, really identify the system, the center of mass for the following objects. And as long as these are uniform masses, the center of mass, or the center of gravity, is actually very simple to find. It's the midpoint, right? It's these points here in the middle. Okay, I try to find the middle as much as I can, but even for this ring, okay, so for the first 3 examples, you can see that the center of mass is contained within the object, but with the ring, okay, it's not contained inside the physical ring. It's contained within the boundaries of the ring. Okay, but as long as this is all uniform, it's going to be the midpoint. Okay, and a lot of times what happens is you'll see something like this. They'll kind of do, that would be this, and here we kind of draw some radii through here. So where all these lines intersect, the bars a little bit, that's kind of where the center of mass is. Okay, and there's a simple rotation lab that you can do for this. If you hang it on a point and let it rotate and draw these lines, in various points, then that's where the center of mass is located. So for example, the center of mass for the United States is somewhere in Kansas. If I believe it, right, because you got like some mountains here, mountains there, you got some other things going on, but now how does this apply for us? Now we're going to do some calculations. So most systems in the universe are not nice and symmetrical, right, which means you need to use some equations to determine the center of mass. And so to find the x-coordinate of the center of mass, you're going to do the sum of mass times position divided by total mass. Okay, and then to find the y-coordinate, the equation is the same. I'm just replacing the x with a y. Okay, and so this allows you to find, let's say, if I have a set of particles like this, right? And so if I have like mass 1, and this is, let's say this is at 0, 0, right, the origin. Okay, if I draw a quick little coordinate system, right? And so you would have like 0, 0, and I call this like 0, 1, call this 1, 1, right? Sorry, it's a bad 1, and this would be like, this would be, I apologize, it's not 1, 1, that would be 1, 0, and this would be 1, 1, right? And so the center of mass, even though this is like going to be evenly distributed, should be in the middle, right? Because if I use this equation, you can find that center of mass. And here on the next page, we're going to do a couple quick little examples looking at this. So here we have 4 objects are situated along the y-axis in this orientation, right? And so here is, and I'm going to draw this in the x, even though this is going to be the y, right? And a lot of times with these center of mass questions, it is helpful to draw a picture. So if this is my origin, okay, so I have a 2 kilogram object that's at 3 meters, right? So that's 3 meters. I have a 3 kilogram object at 2.5 meters. And I'll write the masses above it. So this is going to be 3 kilogram. Sorry, this is 2 kilograms. This is 3 kilograms. Okay, and then I have a mass here. So it's going to be a 2.5 kilogram object at 0. And then I finally have a 4th mass kind of over here. I know this isn't drawn on the scale, at negative 0.5 meters, and it has a mass of 4 kilograms. Okay, so imagine this. So remember, this is our y, right? So imagine turning that up on its edge. So all I really have to do is now simply, if I want to find the y coordinate of the center of mass, all I have to do is sum of mi yi over the sum of the mass. Okay, and so that's basically just going to be 4 times negative 0.5, and yes, make sure you do account for the negative sign. This is the interesting one, the 2.5 at 0 meters. Even though technically it does not necessarily contribute to the center of mass calculation because it's 0 meters away from the origin, the mass does contribute to the total mass. All right, and so I'm going to have 3 times 2.5, and now I have 2 times 3. Right, and I'm going to divide that all over 4 plus 2.5 plus 3 plus 2. Make sure I got all the masses right. Okay, and so this is going to be negative 2, this is going to be 0, this is going to be 7.5, and this is going to be 6. And so what happens is I end up at 11.5, right, in terms of my, if you want to say kilograms times meters, right, and then I've got 4 plus 2.5, which is 6.5, plus 3 is 9.5. Okay, so I have 11.5 kilograms, right, in terms of total mass. Well, that tells me that my center of mass is located at 1 meter. So so it's going to be about, this is going to be my center of mass. Okay, again, I didn't draw this to scale. If I had a nice little grid, that'd be easy to look at, to do. All right, so here's another example. Here we have the, where's the center of mass for the Earth-Moon system, right? And so here's the Earth. Here's the moon, right? And so the way you can expect this, it should be closer to the Earth because of the massive size, right? How massive the Earth is. But if we do the quick calculation, right, and I'm just going to call this is going to be the x direction. It's going to be sum of mixi over the sum of mi. Okay, and so I'm just going to do the mass of the Earth, right, times it's 0 meters away from the Earth, right, plus the mass of the moon, which is all given to you, and it's going to be 3.84 times 10 to the 8th meters, divided by, now even though the Earth is at the origin, remember that mass does contribute, so 5.97 times 10 to the 24th plus 7.35 times 10 to the 22 meters, not meters but kilograms. Erase that real quick. Okay, and so you do your calculation, you're going to find that the center of mass of the Earth-Moon system is at 4.67 times 10 to the 6th meters. So the distance from here to here is 4.67 times 10 to the 6th meters. Now, do pay attention because it talks about Earth-Moon system and it talks about from the center of the Earth. They could have easily talked about from the center of the moon, which means it physically is going to be the same point, But because the moon is involved, you're looking at it from away from the moon, that's going to shift it's going to be further away from the center of the moon. Okay, really all you have to do to make that calculation is just take this number, put it here, right, and flip-flop those two distances, and that's going to give you in terms of from the moon. All right. Okay. Now, everything we've talked about right up until this point is really focusing around right finite systems, right? So we had four particles, we had the Earth and the Moon. Now the I apologize. So the velocity, right, of a center of mass can be determined by simply taking the derivative of the center of mass functions, right? And so basically, if I want to find the velocity of the center of mass, I take the derivative with respect to time of these equations, okay, and you just end up with this equation that says that the velocity of the center of mass is going to be mivi, right? Because xi dt. So think about this: these two are constants, right? And really, you're taking the derivative of the sum of xi, and so it's going to end up with this velocity. So essentially, you replace the xi with a vi, right? And so that would be your x velocity, right? And you can do the same thing with the y velocity, right? I'm going to take the derivative of the y center of mass, or the position of the y, and I end up with essentially the same equation, right? Where again, I'm just flip-flopping the yi and the viy. Okay, and remember, the i's are not initials. These are, right, because if you do anything with a sum, it talks about like I equals 1 to infinity, or however many objects you have. Okay, but one interesting thing is if I do a little bit. So if I take this, I'm just going to do this for the x, right? I'm just going to not. Right, so if I multiply this sum of mi up to here, we're going to get an equation that we're actually going to really look at, right? And I'm going to write the center of mass on the outside, so you don't think I'm going to add those two together. Okay, but this kind of relationship is important for momentum, okay, which is kind of be in our next couple videos. Okay. Now, so to even further complicate things, right, the universe is not necessarily made of just simple systems, right, of two objects, right? The objects tend to have an infinite number of particles, and what we call these objects are called extended objects, right? So just some examples, like a bowling ball is actually technically, in physics 1 we treat it as a single object, but in actuality it's an extended object because, right, there's pieces of the bowling ball missing where the holes where your fingers go and everything. Now, so to determine the center of mass of these types of objects, you're going to need to divide that object into an infinite amount of masses, or amount of areas with masses. Okay, so if I have like just this meter stick, what I do is I take it and break it up into these infinite amount of masses, okay, or areas of masses. Now, because that, if we're talking about, what does this do? Well, that brings integrals into play, right? This idea of summing infinite amount of masses, or infinite amount of intervals, okay? And so to find if it's a finite object, to find the center of mass, we replace that sigma now with an integral. And so we're going to say x dm over, sorry, not just m, but dm. Right? And the y center mass of an infinite object, basically you just flip out the x for a y. Okay? But again, these down here, that leads to your total mass. Okay? Sorry, I'm getting too close to the bottom of the iPad. Okay? Now, locating the center of mass of a long uniform bar is very trivial, right? Because the center of mass, let me highlight that, it's very important. The center of mass okay, is just simply the midpoint of that bar, okay? But again, we're not for, the universe isn't made up of these nice uniformly shaped objects. It's made up of, objects that are, like a baseball bat, where more is going to be towards the barrel of the bat versus the handle. So now if the bar is non-uniform, okay, then it's what we call linear density. Okay, sorry, misspelling this word. Instead of treating it as if I was writing on a piece of paper, let me erase. So the linear density is not constant. And so how do we find the linear density? Okay, well, it's going to be kind of the change of mass, right? So it's like this, taking the derivative of mass with respect to x. Okay, now for a uniform bar, the linear density is just simply mass over x. Okay, if we do a quick little algebraic, change here, okay, and say dm is lambda dx, that's going to help us when we do this next example problem. Okay, all right. So this example problem is going to talk about the mass and location of or the location of the center of mass for a bar length L. Okay, whose whose linear density is given by the equation lambda equals bx squared, where b is a constant coefficient and x is the distance from the left end of the bar, right? And so here's my bar. So x is kind of like any distance, right, from the left end of the bar. So this is going to be our origin, okay? And we know it's not going to be, it's a non-uniform bar because we're given an equation for lambda, okay, which tells me that I have to use these integrals we just talked about in some way. So the first thing I need to do is essentially find the relationship for mass. And so that's where I'm going to use this dm equals lambda dx equation. That is kind of like, I didn't necessarily just throw it out there. We did it for a reason. Okay. Now in calculus, if we want to get rid of these d's, right, those d's are kind of representative derivatives. If we want to get rid of them, we take integrals. And so what happens is the mass of the bar is going to be given by the integral of the linear density dx, and that's going to be from 0 to L, the length of the bar. Okay, and they give us the equation for lambda, so it's bx squared dx evaluated from 0 to L. And so we do bx cubed over 3. We evaluate that from the 0 to L, which tells me my mass. And again, that's going to be the first part of this question because it says find the mass, right? So the mass is going to be given by bl cubed over 3. Okay. Now, the next part, right, is to find the location of the center of mass. And so we're going to use the integral equation, so the integral of x dm over dm. Well, we found the integral of dm. That is our mass, which was bl cubed over 3. Now what we have to do is the top part, is this integral of x dm. Okay, and so what happens is that goes back to the linear density, right? So what I'm going to do is I need to find something for dm, but I have it again right here. This dm equals lambda dx. And so if I rewrite that, I say x lambda dx. Okay, but I know what lambda is. It's that bx squared, right? I'm going to do the integral of that, and I do some kind of simplifying here. So this becomes bx cubed dx, right? So the integral of bx cubed is going to be bx to the fourth over 4. Again, though, we're going to evaluate all this from 0 to L, from the origin to the length of the bar. But that's very easy because then the top part just simply becomes bl to the fourth over 4. And so what I'm really going to divide is these two expressions, right? bl to the fourth over 4 divided by bl cubed over 3. And so, excuse me. So what happens is b's cancel. Those, sorry, I didn't mean to cancel all that. But what happens is these 3 cancel 3 of those. And so I end up with L over 4 over 3. And I do a little bit of algebra, right? And so this ends up being 3L over 4. Okay, and so that's the location of my center of mass. Okay, now I know this video is long, right, because center of mass is actually a new concept, and there's an idea where we bring in some calculus to it. What we're going to do in the next video now then is focus on linear momentum. Now for some of you guys that are watching these videos, this may be a review, especially if you've taken AP Physics 1. If you have not taken AP Physics 1, this will be a new concept for you.